GCE Advanced Level Chemistry Practical Series, experiment number 7. Experimental determination of the enthalpy of acid-base neutralization. In this experiment, we are going to be taking a look at a few acid-base neutralization reactions that involve sodium hydroxide and HCl acid-base reaction, potassium hydroxide and nitric acid, sodium hydroxide and ethanoic acid, and ammonium hydroxide and HCl acid-base reactions will be observed in this reaction. Aims of this experiment is to learn how to measure temperature changes that are taking place when we are carrying out an acid-base reaction, and to determine the neutralization enthalpy of acid-base reactions experimentally. So students, we are going to learn through this experiment how to determine and how to carry out calculations to find out the neutralization enthalpy of acid-base reactions. So let's take a look at the introduction, students. Most of the physical and chemical changes that we are carrying out in the lab are carried out under constant pressure conditions. Now, what does that statement mean? When it comes to carrying out reactions in the lab, we often carry out reactions in beakers, test tubes, boiling tubes, and all of them are open to the atmosphere. We don't do reactions in closed or sealed off containers for the most part. So majority of the time when you're mixing reagents to carry out especially acid-based titrations or acid-base reactions, we leave the system open to the atmosphere. So therefore, we leave the system subject to the atmospheric pressure. So we are carrying out these reactions under a constant pressure conditions. Why? As the atmospheric pressure does not change drastically within the span of our reaction, we will consider it to be a constant pressure. In the laboratory, for example, reactions are generally carried out in beakers, flasks or test tubes that remain open to their surroundings and hence to the pressure of approximately 1 atm or 1 atmosphere. So students, we leave the system open to the surrounding. So therefore, the pressure that the system feels is going to be 1 atm. For example, if you show it with a diagram here, if you take a beaker, so this is our reaction mixture. This is where the reaction is taking place. And students, we leave the system open to the surrounding. So because of that, whatever the atmospheric pressure is the pressure that is experienced by our system here. And it's going to be a constant pressure, as the atmospheric pressure does not change drastically over the period of the time that we actually carry out this experiment. So when we are carrying out an experiment, we are actually carrying out this experiment at a constant pressure of 1 atm approximately. To quantify the heat flow into or out of a system at a constant pressure process, chemists use a property called enthalpy, represented by the symbol H. So students, when we are talking about a chemical reaction, apart from the chemical changes that are taking place in the system, there's another change that is taking place. That is the energy changes. Majority of the chemical processes that we are going to be observing are going to involve energy changes. As matter undergoes chemical changes, there will also be an energy change. So when you are carrying out a reaction, especially a neutralization reaction, you will observe the system heating up. If you ever carry out an acid-base reaction in a test tube or a boiling tube, as you mix the two reagents together, you would feel that the energy system is heating up. You will feel the heat if you touch the test tube or the boiling tube, or maybe the beaker that you're carrying out the experiment in. So this means there's a certain amount of energy released from the system. And there are certain reactions that will cool down the system. When you're carrying out a reaction, you might have observed sometimes the system cools down, right? So when we are going through other practicals, you would notice these types of endothermic reactions as well. So when it comes to a system, when we are carrying out a reaction in a system, there's going to be an energy change. And if this energy change that is taking place in a reaction is happening at a constant pressure, this measured energy change or heat exchange is going to be given a special name called enthalpy. So we consider it to be enthalpy if the measured energy change was measured when the system was undergoing a reaction at a constant pressure. If the pressure remained a constant and the energy that is going to be released or absorbed is going to be considered to be enthalpy. So let's take a look at that sentence again. Over here, they have mentioned, this is a very important statement, to quantify the heat energy flow into or out of the system in a constant pressure process, chemists use a property called enthalpy. A property called enthalpy would be used. And it is represented by the symbol H. At constant pressure, chemists use the relation heat energy is equal to enthalpy. So whatever the heat energy at a constant pressure that is going to be exchanged is equal to enthalpy change, or heat energy of a substance is equal to enthalpy. However, students, measuring the enthalpy of each individual substance that is going to be in the reaction mixture or in the system is not possible. So therefore, what we are going to be doing is measuring the energy change that takes place when we are carrying out a reaction. When we mix acid and base together, you will see the certain amount of energy is exchanged. This results in a temperature increase in the system. When it comes to acid-base reactions, that is what you will observe. And there are certain other reactions when you mix the two reagents together, the system will cool down. Again, this is also an energy exchange. So instead of measuring the enthalpy of each individual substance that is going to be present in our system, we can easily measure the energy change or the heat change that was taking place when we are carrying out a reaction. So this energy change or heat change that we measure under constant pressure conditions are known as enthalpy changes. So it is easier to measure enthalpy changes than going in to measure the exact enthalpy of each individual substance. So let's take a look at that statement here. The enthalpy is an extensive property. That's also a very important observation. Enthalpy is an extensive property. That means its magnitude will depend. Uh, on the amount of the substance that is present, and it is impossible to determine the enthalpy of a substance. However, we can measure the change in enthalpy. We can't measure the enthalpy of a substance experimentally. However, we can measure the enthalpy change. When the enthalpy change, or whenever you are carrying out a reaction, when two reagents react together, releasing energy at a constant pressure condition, that energy released or energy absorbed is going to be your enthalpy change. So that enthalpy change can be measured. However, each individual enthalpy of the substance cannot be measured. When the two things are reacting, the energy release will lead to us measuring the enthalpy change of the reaction. And enthalpy change is denoted by delta H. Right, so we can accurately measure delta H. So they say in this particular sentence, enthalpy change is a extensive property indicating that the amount of substance that we have reacting in a reaction mixture will determine the enthalpy change of that particular mixture, and it is impossible to determine the enthalpy change of a substance, so it is the change in enthalpy that we accurately measure. Right, students? So we learned a few things about enthalpy here. I hope you remember them by now. We learned enthalpy is the heat of a system measured at constant pressure conditions. So afterwards we learned enthalpy is an extensive property. That means it depends on the amount of substance present in the system. The more substance you have, the more enthalpy you will observe in the system. And we also learned we cannot measure the enthalpy of each individual substance. However, we can measure the enthalpy change. When a substance is undergoing change, the heat energy absorbed or released is going to be, we can measure the heat energy absorbed or released under a constant pressure, and that type of heat energy that is absorbed or released in a chemical process at constant pressure is known as enthalpy change. So enthalpy change can be measured, but not enthalpy. The enthalpy change of a reaction, delta HRXN is the difference between the enthalpies of the products and enthalpies of the reactants. Right? So we can't measure the enthalpies of products and reactants experimentally. However, if you know the enthalpies of product and reactants, if you know the difference between them, that will give you the enthalpy change. Right. So now students, this is the equation for enthalpy change. We now move on to the definition of heat. As the enthalpy is equal to the heat at a constant pressure, we may consider the measurement of heat changes. In the laboratory, the heat changes in physical and chemical processes are measured with a calorimeter, a closed container designed specifically for this purpose. And to estimate heat changes, we first need to have an understanding of specific heat and heat capacity. Now students, when you're carrying out this type of experiments, it's very important to have a good understanding of heat changes and how they are going to be equal to enthalpy changes. As we carry a chemical reaction, or in this particular experiment we are carrying out a neutralization reaction, there's going to be an energy released in the neutralization reaction, and the energy that is released in the form of heat energy. So students, this experiment is going to be done at a constant pressure environment, or we can simply say it is exposed to the surroundings. So therefore the system is at 1 atm pressure. So because of that, enthalpy is equal to heat at constant pressure. So heat change that takes place at constant pressure is equal to enthalpy change. Enthalpy is basically the heat at constant pressure, and enthalpy change is the heat change at constant pressure. And when we are moving on with this experiment, it is very important to know these two terms: specific heat capacity or specific heat, and heat capacity. Specific heat and heat capacity are two very important phrases that you should be aware of. So this is important for us to estimate the heat changes that takes place in a system. We should know these two phrases. So now let's take a look at the definitions of specific heat and heat capacity. Specific heat, normally denoted by a simple C. The specific heat of a substance is the amount of heat required to raise the temperature of 1 gram of substance by 1 degree of Celsius or Kelvin. Now students, you would have learned in school, when you are learning about this lesson, the specific heat is the amount of energy needed to raise the temperature of 1 gram of substance by 1 degree Celsius or 1 degree Kelvin, as the magnitude of 1 degree of Celsius and 1 degree of Kelvin is both the same. So you can take 1 gram of substance and you can measure the energy that is needed to increase the temperature of that 1 gram of substance by 1 degree Celsius. And the energy needed to do this is known as specific heat capacity. So if you take water, for example, if you take 1 gram of water, if you take exactly 1 gram of water, the amount of energy needed to increase the temperature, let's say now this water is at 25 degrees Celsius, the amount of energy needed to increase the temperature from 25 degrees to 26 degrees Celsius. So this is the difference. Difference is going to be 1 degree Celsius, right? So the amount of energy that we should be giving to increase the temperature by 1 degree Celsius is known as specific heat capacity. So the amount of energy you should actually be giving to increase this temperature of 1 gram of water by 1 degree Celsius is roughly around, for water, is going to be 4.2 joules per Kelvin is going to be the unit. Joules per Kelvin per gram. Joules per Kelvin per gram is the unit. Joules per Kelvin per gram. This would indicate for a single gram of water to increase the temperature by 1 degree Celsius or 1 degree Kelvin, you would need 4.2 kilojoules of energy. So the amount of energy that you should be giving is 4.2 joules of energy. You should give 4.2 joules of energy to increase the temperature of 1 gram of water by 1 degree of Celsius. You might have also learned that specific heat capacity can be communicated in the following way as well. That is, if you take 1 kilogram of substance, instead of 1 gram, if you take 1 kilogram of substance, the amount of energy needed to increase the temperature by 1 degree Celsius, or 1 degree Kelvin, is known as specific heat capacity as well, right? For example, the delta T value or temperature change that has taken place over here is just 1 degree Celsius. So specific heat capacity is defined this way as well. The amount of energy needed to increase the temperature of 1 kilogram of substance by 1 degree of Celsius or 1 Kelvin. So over here, if this is water, the amount of energy that should be given to increase this 1 kilograms of water's temperature by 1 degree Celsius is going to be 4,200 joules. So the specific heat capacity of water can be written as 4,200 joules per Kelvin per kilogram. So you can leave the specific heat capacity in these units as well. Now students, earlier on we learned when it comes to specific heat capacity of water, it can be communicated in joules per Kelvin per grams. So that value was 4.2, right? That means to increase the temperature of 1 gram of water by 1 degree Celsius, we needed to give 4.2 joules of energy. But also we can use this form of specific heat capacity of water, right? When it comes to 1 kilogram, how many grams are there? 1000 grams is 1 kilogram. So when it comes to conversion of the specific heat capacity of water, which is 4.2 grams or joules per Kelvin per gram, into joules per Kelvin per kilogram, you have to multiply that by 1000. So 4.2 multiplied by 1000 is 4,200 joules per Kelvin per kilogram. So both ways are correct. So over here we have very clearly shown you specific heat capacity of water can be communicated this way as well. We have very clearly shown you here the specific heat capacity of water can be communicated as 4.2 joules per Kelvin per gram. That means we have taken 1 gram of water and measured how much of energy is needed to increase the temperature of this 1 gram of water by 1 degree of Celsius, and the energy needed to make that change happen is 4.2 joules. But when we increase the mass of water to 1 kilogram, the energy that was needed increases by 1,000-fold. So the energy needed to increase the temperature of 1 kilogram of water by 1 degree Celsius happens to be 4,200 joules per Kelvin per kilogram. So now we have had a good look at specific heat capacity. Let's move on to heat capacity. The heat capacity of a substance is the amount of heat required to raise the temperature of a given quantity. That's very important, students. Raise the temperature of a given quantity, not a specific quantity like 1 gram or 1 kilogram. Those are unit masses. Here we are talking about the amount of energy needed to increase the temperature of a given amount of mass by, or given quantity, by 1 degree Celsius. Right, so let's go over the definition again. The heat capacity, which is often indicated by capital C, of a substance is the amount of heat required to raise the temperature of a given quantity of the substance by 1 degree Celsius. Specific heat capacity is an intensive property. That means it does not depend on the amount of substance that is there, right? Intensive properties are properties like boiling point of water. No matter how much water you have, the boiling point of water is always going to be 100 degrees Celsius. So similarly, when it comes to specific heat capacity of water, no matter how many grams of water you have, the specific heat capacity of water is going to be 4.2 joules per Kelvin per gram. However, heat capacity is an extensive property, which means it changes with the amount of substance or mass of the substance you have. The relationship between the heat capacity and specific heat is given over here. So you can take a look at this equation. Heat capacity is equal to mass multiplied by specific heat. Heat capacity is equal to mass multiplied by specific heat. Sometimes S can also be used to denote specific heat, right? Since both heat capacity and specific heat are using letter C as their symbol, to avoid confusion, in certain instances we use S instead of simple C to denote specific heat capacity. Knowing that specific heat and the amount of substance, the change in the sample's temperature delta T, the amount of heat that has been absorbed or released in a particular process can be calculated by the following equation. So students, what this sentence says is, if you know the specific heat of a substance and the amount of a substance, basically if you know the amount of substance or the mass of overall substance you are using for this experiment, and if you know what type of temperature change you observed when the reaction was taking place, if you know all these three things, we can calculate the amount of heat, which is usually denoted by Q, that has been absorbed or released by the system when the reaction was taking place. And that equation is given here. Q is equals to mc delta T, mass multiplied by specific heat multiplied by temperature change. Or sometimes we use mc delta T, or T can be capital. Either form of this equation is correct. And when you are measuring the temperature, temperature can be measured in Celsius. Actually, it's not 0 C, it's Celsius. So we'll correct that here. It's Celsius, or delta T in Kelvin. So keep in mind, students, when it comes to temperature changes, Celsius and Kelvin, since 1 unit or 1 Celsius is going to be equal to 1 Kelvin, the temperature changes are usually both equal when you're talking about delta T values or temperature change values. Temperature change values in Celsius or in Kelvin are both going to be equal to one another. So just to emphasize on that a little bit, so we'll talk about the two scales here. Temperature change in Kelvin, let's say this is Kelvin, and what we have above is Celsius. So our Celsius scale, we usually start talking about it from 0 position over here. At that point, students, the Kelvin value that is equivalent to 0 degrees Celsius is 273. And you usually follow this trend whenever you want to convert Celsius values into Kelvin. How do you do that? So for example, if you want to convert 25 degrees Celsius into Kelvin, you usually do this: 273 plus 25 degrees, or 25. And then you write the Kelvin value is 298 Kelvin. So if you were doing this and you didn't know why you were doing this, this is because 1 degree of Celsius and 1 degree of Kelvin, or 1 Kelvin, are equivalent in magnitude. That means when you're moving to 1 degree of Celsius, right? 1, 2, 3, let's say. Kelvin values will vary the following manner: 274, and over here we have 275, and over here we have 276. So the gap between, or the magnitude of 1 Kelvin and magnitude of 1 Celsius is the same. However, when Kelvin is at 273, at that point our Celsius scale starts. So that is why whenever we have a Celsius value, when you want to convert into a Kelvin value, we will add 273 to that particular Celsius temperature value. And if you go to the other extreme over here, where our Kelvin scale starts, Kelvin 0 is going to have a Celsius value of minus 273 degrees Celsius. So I hope this actually gives you an idea about why the temperature changes can be measured in both Celsius and Kelvin, and they happen to be the same value. Right? For example, when we are moving from let's say 0 degrees to 3 degrees Celsius, over here the change in temperature was 3 degrees Celsius. And if you are talking about the temperature change in Kelvin, over here 1, 2, 3 Kelvins have increased from 273 to 276. So temperature difference happens to be the same number. Although the unit is different, the magnitude is the same. In this case, 3 Kelvin temperature difference is equivalent to 3 Celsius temperature difference. I hope this is clear to you by now. So now we have learned what equation we can use to measure the amount of heat that has been absorbed by the system or released by a system. Now students, when certain chemical reactions are taking place, energy is going to be released. You will notice, as certain chemical reactions are taking place, energy is released. How do you observe this energy release? The container or the solution heats up. Right? If you are mixing acid and a base in a beaker and you have a thermometer in the solution, you will see both acid and base usually will be at room temperature. When you mix the two up, when the reaction is taking place, you will observe the temperature rises above the room temperature. Right? So this means the temperature of the solution has gotten increased. Why? Because as the reaction was taking place, energy has been released into the system, increasing the system's temperature. So these type of reactions that are releasing energy are known as exothermic reactions. And since exothermic reactions are going to end up releasing energy, if you remember our enthalpy change equation, delta H is equal to product's energy minus reactant's energy. So these two reactants have released some of the energy they had. So the product obviously would have lower amount of energy than the energy seen in both of these reactants. As reactants react, if some of their energy is released, then the product will have less amount of energy, right? So we are starting with a high amount of energy and they end up giving some energy off or out of the system. So because of that, the products will have lower amount of energy. So product minus reactants enthalpy would be a negative value. Product minus reactants enthalpy would be a negative value. So you have to keep in mind when it comes to exothermic reactions. For exothermic reactions, the enthalpy value is indicated as a negative value. And that equation can be given this way: delta H is equal to heat that you calculated divided by moles of the reactant that was acting as a limiting factor. Now when you are carrying out a reaction, there will always be a reactant that is going to be acting as the limiting factor. So Q divided by the moles of reactant acting as a limiting factor. Very important piece of information that should not be missed when it comes to this equation is that there is a negative sign here. There's a negative sign here. This is because when it comes to an exothermic process, heat is released and enthalpy values that are calculated are going to have a minus sign or negative sign. So you need to have this negative sign in the equation. And then we have for endothermic processes. For an endothermic process, you will have, let's say, X and Y reacted to produce Z. So there are certain processes that will absorb energy as the reaction takes place. Right? So there are certain processes that take in energy as reaction takes place. So X and Y, let's say they start with certain amount of enthalpy or energy, it is going to be present in Z because it didn't lose any energy. Apart from that, it has taken more energy from the surrounding. Then what happens? If X and Y energy is present in the product as well as some additional energy going into the system is present in Z, the product's energy is going to be greater than reactant's energy, right? So because of that, when you calculate enthalpy change with the use of the equation delta H is equal to product enthalpy minus reactant's enthalpy, you will get to a positive value as product's enthalpy are going to be greater because we have now taken additional energy from surrounding when forming the product. So product's enthalpy is going to be greater than reactant's enthalpies. So product minus reactant enthalpies are going to be positive values. For endothermic reactions, enthalpy value is indicated as a positive value. The enthalpy change is given by this particular equation. But before we go into the equation, let's take a look at what is taking place here. We have X plus Y turning into Z. Now, imagine for this reaction to take place, it requires energy from the surrounding. Let's say that it absorbs energy from the surrounding. So at that point, students, the product's enthalpy or energy that the product has would be greater than the energy that was observed in both of these XY reactants. Why? Apart from their energy, we absorbed energy from the surrounding and we placed it in the product Z. So therefore, product energy or enthalpy is greater than reactant enthalpies. So when you're calculating the delta H, we use the formula product enthalpy minus reactants enthalpies. Since the product enthalpy is much greater than the reactant enthalpies, the overall value is going to end up being a positive value for such an enthalpy change. So that is why, students, we have this particular equation. You need to observe that the sign over here is a positive sign. Delta H is equal to the energy change that you measure divided by the moles of the reactant. We are normally taking the moles of the reactant that acts as the limiting factor. So Q divided by the moles of the reactant. Usually the reactant that is acting as the limiting factor is taken here. So one thing that you should not miss is a positive sign in this equation. Now, after observing that, let's move on to the next slide. So macroscopic properties. So a small introduction to macroscopic properties and intensive and extensive properties. The properties which are associated with the bulk or macroscopic state of the system, such as pressure, volume, temperature, concentration, density, viscosity, surface tension, a refractive index, color, etc., are called macroscopic properties. So these are basically examples and the definition of macroscopic properties. And macroscopic properties in a system usually can be divided into two types. There are two types of macroscopic properties, and that is our main interest here, students. So first one is extensive properties. Now, extensive properties are properties that depend on the amount of substance or the size of the system. As the amount of substance increases, the extensive property values will also change. For example, if you take a larger and larger amount of moles of a substance, the mass of that particular substance will increase. So mass is a extensive property. The properties that are depending on the size of a system are called extensive properties. For example, volume, the number of moles, mass, energy, internal energy, etc. are given as extensive properties. The value of the extensive property is equal to sum of the extensive properties of smaller parts which a system is divided. Suppose the mass of M1 is 1 gram, or M1 is given in grams, M2 is given in grams, and M3 also is given in grams, and these three portions of substances are mixed together. Then that particular system has an overall mass of M1, M2 and M3. So to simplify this for you, imagine you take a beaker. We'll say the weight of the beaker is negligible here. So, and we are creating a system by mixing M1 amount of grams of one reactant, M2 amount of grams in another reactant of another reactant, and finally we are adding a third reactant, let's say that has a mass of M3 grams. After the addition of all of these reactants, the overall mass of this reaction mixture is going to be M1 plus M2 plus M3 grams. So this is how extensive properties behave. When smaller parts of a system come together, the overall value of the extensive property will change. So that's what it says here. Now take a look at that sentence again. The value of an extensive property is equal to sum of the extensive properties of smaller parts into which the system is divided. And then over here they have gone further. Total mass of the system is equal to this. Thus, mass is an extensive property. Apart from mass, volume is going to act as an extensive property. Amount of number of moles or amount of moles, enthalpy are going to be considered as extensive properties. So each of these things depend on the bulk or depend on the amount of substance or the size of the system. As the size of the system changes, the value of this extensive property will also change. Intensive properties. The properties that are independent of amount or size of the system are known as intensive properties. For example, refractive index, surface tension, density, temperature, boiling point, freezing point, these things are independent of amount of substance. Like I mentioned earlier, a good example would be boiling point of a substance. Boiling point of a substance does not depend on the amount of that substance. If you take 100 milliliters of water or 1000 milliliters of water, they both will start to boil when they reach a temperature of 100 degrees Celsius. So the boiling point of water or boiling point of any substance does not depend on the amount of substance. It depends on what kind of substance we are dealing with. So it doesn't depend on amount or the size of the substance. And these type of properties are known as intensive properties. Other examples, density. If you take density for any material, again if you take water, 1 gram per cubic centimeter is the density of water. If you take 1 gram, the density is 1 gram per cubic centimeter. If you take 100 grams, the density of water still remains the same, right? It doesn't change. Even in 100 grams, the density of water still remains 1 gram per cubic centimeter. So students, a density of water or density of any substance, we are taking water as an example, is not going to be dependent on the mass or the size of the system. Temperature, boiling points, surface tension, refractive index, freezing point, all of these properties that are listed here as examples are intensive properties. These properties do not depend on the number of moles of the substance in the system. If any extensive property is expressed as per mole, very important sentence here. If any extensive property is expressed as per mole or per gram or per cubic centimeter or per square centimeter, it becomes an intensive property. So if you take any extensive property and communicate it with these units, right, per mole, per gram, per cubic centimeter or per square centimeter type of unit, you convert it into a intensive property. Let's take a look. Example, mass, volume, heat, capacity are extensive properties, but when you communicate it in relation to a unit or per unit, you will observe them turning into intensive properties. For example, when you communicate the mass of a unit volume, we call it density. Mass in itself is an extensive property. However, when you communicate mass per unit volume, it becomes density, and density is an intensive property. Volume is an extensive property. However, if you communicate volume as volume per 1 mole of substance, then it becomes molar volume, and that is an intensive property. And we have a specific heat capacity, that is also an intensive property. Specific heat capacity is the amount of energy needed to increase the temperature of a substance by 1 degree of Celsius, and the amount of substance we take is fixed. So we take either 1 gram or 1 kilogram for a unit mass. But when it comes to heat capacity, we don't take a specific unit mass. We take whatever the mass of that particular substance and observe the amount of energy needed to increase the temperature of that substance by 1 degree Celsius. So heat capacity is essentially an extensive property, while specific heat remains an intensive property. So density, as I mentioned earlier, molar volume and specific heat are intensive properties, while mass, volume and heat capacity are extensive properties. And one good example is given over here. Specific heat capacity of water is this, 4.184 joules per gram per Celsius, or you can communicate it as joules per gram per Kelvin. However, if you take a look at the heat capacity of 100 grams of water, it happens to be 418 per 0.4 joules per Celsius. Now, how did we get to this point? We use this equation. Heat capacity, capital C, is equal to mass of the substance multiplied by specific heat capacity of the substance. So specific heat capacity is a constant value, it doesn't change. However, if we increase the mass of this substance, heat capacity of that substance will also increase. That means heat capacity dependent on the mass of the substance. So anything that depends on the amount or the mass of a substance is usually an extensive property. So specific heat capacity, simple C, specific heat capacity is an intensive property, while heat capacity is an extensive property. And you can observe that with the units as well. When it comes to heat capacity, the unit is joules per Celsius. So there's no unit mass or unit volume given here, or unit area given here. So this is just joules per Celsius. And when it comes to specific heat, it is joules per Celsius per gram, right? So the unit mass is coming into play here. So specific heat is going to be a intensive property. Now let's move on to the next slide. Standard enthalpy change of neutralization. Let's note new. So enthalpy change of neutralization, or standard enthalpy change of neutralization, is the enthalpy change when 1 mole of aqueous H plus ions and 1 mole of aqueous OH minus ions in the standard state react to form 1 mole of liquid water. And what is standard state? When H plus ions and OH minus ions are reacting at 1 atm pressure and 25 degrees Celsius in their aqueous form, it is going to be considered as their standard state. And when it produces 1 mole of water, liquid water, as per this definition, the energy change that you observe is going to be known as your standard neutralization enthalpy. Standard enthalpy change of neutralization. So whatever that we have written over here in words are given here in the equation as well. So H plus aqueous and OH minus aqueous ions that are reacted at 1 atm pressure and 25 degrees Celsius. When they react, when it forms 1 mole, very important students, we take 1 mole of H plus and 1 mole of OH minus in 1 atm pressure and 25 degrees Celsius. When you react these two together, you produce 1 mole of liquid water. And the energy change or enthalpy change that is observed in this reaction is going to be known as the enthalpy change of neutralization, negative 57 kilojoules per mole. And so the negative sign over here indicates that as this reaction took place, the energy change that happened was basically an energy release. So basically this is an exothermic reaction, students. As this reaction took place, energy was released. Energy was released. As this reaction took place, energy was released, and overall neutralization enthalpy, standard neutralization enthalpy for this particular reaction is going to be minus or negative 57 kilojoules per mole. Negative 57 kilojoules per mole, and the negative sign indicates that this particular reaction was an exothermic reaction. Some neutralization enthalpies of strong acid, strong base reactions are given over here. For example, when you have sodium hydroxide 1 mole reacting with 1 mole of HCl, you produce 1 mole of water. 1 mole of water. You can see HCl has an H plus that is going to be released. HCl is a strong acid. Strong acids easily dissociates in water to produce. If you put 1 mole of HCl into water, 1 mole of H plus and 1 mole of Cl minus will be produced. So we have 1 mole of H plus here in aqueous form and 1 mole of hydroxide ions in aqueous form. Sodium hydroxide is a strong base, and when we add sodium hydroxide to water, it will completely dissociate into Na plus and OH minus ions. So 1 mole of sodium hydroxide means 1 mole of OH minus ions are present in the medium. So 1 mole of OH minus, 1 mole of H plus will produce 1 mole of liquid water. And that is what is usually taking place in a neutralization reaction. So the energy change when 1 mole of H plus and 1 mole of OH minus react in standard conditions to produce 1 mole of liquid water is minus, or enthalpy change is going to be minus 57 kilojoules per mole. And you can see that enthalpy change here. So another strong acid, strong base, potassium hydroxide and HCl. Again, you have 1 OH minus moles here and 1 H plus moles here coming from HCl. And when you add them together, the main ionic reaction that is taking place over here is H plus and OH minus reacting together to form H2O. And 1 mole of H2O will be produced. So what is the enthalpy change when 1 mole of H plus and 1 mole of OH minus react in standard conditions to produce 1 mole of liquid water? What is the enthalpy change? Minus 57 kilojoules per mole. You see it here as well. And if you took another example between a strong base and a strong acid, you will observe the same enthalpy change. So why is this? First of all, we'll make note of this observation. Any strong acid, strong base neutralization will have a standard enthalpy change of neutralization of negative 57 kilojoules per mole. So the enthalpy values for neutralization of strong acids and strong bases are going to be negative 57 kilojoules per mole. So these values are negative, of course, as neutralization reactions are going to be exothermic. And when it comes to strong acids and strong bases, students, they are given the name strong because these strong acids and strong bases are fully dissociating in water. So if you take 1 mole of sodium hydroxide and add it to water, all of that 1 mole of sodium hydroxide will dissociate easily into Na1 plus and OH1 minus ions. So there will be 1 mole of hydroxide ions available in that aqueous medium. And if you add another solution that contains 1 mole of HCl, in that solution 1 mole of H plus ions will be present. So students, because of this, when you react OH minus and H plus 1 mole of each, you will produce 1 mole of water. So this is the definition, according to the definition of neutralization enthalpy. When 1 mole of OH minus and 1 mole of aqueous H plus ions react together to form 1 mole of liquid water, the energy change is going to be negative 57 kilojoules per mole. And you can see that happening in every strong acid, strong base reaction. So now let's observe some other neutralization enthalpies of different acids. We have acetic acid reacting with sodium hydroxide, and you can see acetic acid has 1H plus that can be released, and sodium hydroxide has hydroxide ions. So when you mix 1 mole of acetic acid and 1 mole of sodium hydroxide, you will produce 1 mole of liquid water. So a neutralization reaction takes place. However, if you observe the neutralization enthalpy of 1 mole of acetic acid, it is not 57 kilojoules per mole, right? Why would that be? This is because, students, acetic acid is a weak acid, and acetic acid would require some energy to fully dissociate in water. In water, only a small portion of the acetic acid is present as H plus ions and acetate an ion. As sodium hydroxide is added, these H plus ions that are freely available will react with sodium hydroxide to form liquid water, but the main portion of H plus ions are still present within the undissociated acetic acid molecules. So these acetic acid molecules need to dissociate, and that dissociation requires energy. So from some of the energy that is released in the neutralization process, some of that energy is taken back in to dissociate the acid completely. So that is why this dissociation value is not as high as negative 57. Instead, it is negative 55. So the amount of energy released over here is less. Why do we record that the amount of energy released when it comes to neutralization of a weak acid is going to be less? Because some of the energy that is released when 1 mole of water is produced is actually absorbed to break the undissociated weak acid molecules. So when you're forming 1 mole of water, in actuality 57 kilojoules per mole of energy is released. However, we will not record that energy release because we will use some of that energy to break the undissociated acids to release the H plus ions. So this is the situation with any weak acid strong base reaction or a weak base strong acid reaction. You can see over here as well, when you are reacting weak acid, here we have propanoic acid. So earlier we looked at ethanoic acid. This is propanoic acid. You will see propanoic acid when reacted with sodium hydroxide also, you will have 51 kilojoules of energy released. So because of that, the enthalpy change is going to be given as negative 51 kilojoules of energy, kilojoules per mole of energy. Again, the neutralization enthalpy of this particular weak acid with a strong base is not going to be recorded as a negative 57 kilojoules per mole. Instead, it is negative 51 kilojoules per mole. This again is because some amount of energy was reabsorbed to dissociate these weak acids completely. The same can be said about weak bases as well. You can see a strong base with a strong acid. A neutralization will result in giving off 57 kilojoules per mole of energy. So the enthalpy change of neutralization of 1 mole of sodium hydroxide would be negative 57 kilojoules per mole. However, when you're trying to neutralize 1 mole of ammonium hydroxide, which happens to be a weak base, with a strong acid, HCl, when you're trying to neutralize 1 mole of weak base with a strong acid, which is HCl, you will see the neutralization enthalpy of 1 mole of ammonium hydroxide is not 57. Instead, it is negative 55 kilojoules per mole. Negative 55 kilojoules per mole. So again, this indicates that the dissociation of the base required some amount of energy, and that energy was obtained through the energy released when the neutralization of the base was taking place. So that is why the neutralization enthalpy that we find experimentally happens to be 55 kilojoules per mole when we are calculating the neutralization enthalpy of a weak base like ammonium hydroxide. So what I mentioned previously is mentioned here as well. Explanation for the disparity is seen above between a strong acid neutralization and weak acid neutralization, and strong base neutralization and weak base neutralization is given over here. For example, if you take the weak acid, we see weak acid, ethanoic acid or acetic acid, has a neutralization enthalpy of negative 55 kilojoules per mole, and strong acid neutralization has a neutralization enthalpy of negative 57 kilojoules per mole. This is a more exothermic enthalpy value, or the amount of energy released is greater. The negative sign indicates whether it was exothermic or endothermic. The magnitude of the value indicates how much of the energy was released. So over here, greater amount of energy is released apparently when a strong acid is reacting. Why is this? The value of enthalpy of neutralization depends on the strength of the reactant acids and bases in a particular reaction. So the neutralization enthalpy depends on whether we are dealing with a very strong acid or whether we are dealing with a very weak acid, or strong base or a weak base. The enthalpy change of neutralization involving a weak acid or weak acids are smaller in magnitude compared to that between strong acids and strong bases. Yes, we made that observation earlier. Enthalpy change of neutralization involving weak acids or enthalpy change of neutralizations involving weak bases are usually going to have a smaller enthalpy in magnitude compared to strong acids and strong base neutralizations. This is because weak acid or weak bases are partially dissociated. Very important. They are partially dissociated, which means not all hydrogen ions when it comes to weak acids, and when it comes to weak bases, not all OH minus ions. So since we are talking about weak acids mainly here, this means not all hydrogen ions are free to react with hydroxide ions. Some energy is required to break the chemical bonds in weak acids to produce hydrogen ions. So students, as you can see in the equation that is given over here, the ethanoic acid will only partially dissociate into H plus and ethanoate an ion. Actually, only a very small amount of H plus will come into the medium. Majority of the ethanoic acid molecules will remain undissociated. So, when you are trying to carry out a neutralization reaction, we are trying to react 1 mole of this acid with 1 mole of a strong base. That means all of the acid should react. Not only the H pluses that are dissociated here, but also the H pluses that are not yet dissociated should be taken out for the reaction to take place. That would mean the molecule should dissociate and release H plus. This dissociation of undissociated ethanoic acid molecules would require additional energy, and this additional energy is taken through our neutralization reactions. When these H pluses are reacting, they will release certain amount of energy, and that energy will be taken back into breaking these undissociated ethanoic acid molecules. For example, at equilibrium, only a small amount of the acetic acid or ethanoic acid molecules are dissociated. Most hydrogen ions are still bound to acetic acid. The forward reaction of this dissociation is endothermic, as denoted by the delta H positive value. See, we have indicated that here. The dissociation enthalpy of this weak acid is a positive delta H value, indicating that it is an endothermic reaction. So this is why when weak acid are reacted with strong bases and we calculate the neutralization enthalpy of a weak acid, it happens to be smaller in magnitude compared to the neutralization enthalpy of a strong acid, strong base reaction, because some of the energy that is released in the neutralization reaction are taken back into dissociating the weak acid further. So over here in this table, we can see acid-base neutralization reactions and the neutralization enthalpy for 1 mole of the acid or the base. So when you are carrying out this neutralization reaction between HCl and sodium hydroxide, the neutralization enthalpy is negative 57 kilojoules per mole, and we knew that already. When you're reacting nitric acid 1 mole with sodium hydroxide, so nitric acid's neutralization enthalpy is going to be 57 kilojoules per mole. HCl neutralization enthalpy is 57 kilojoules per mole. When it comes to sulfuric acid, however, when you are trying to find out the neutralization enthalpy of 1 mole of sulfuric acid, it happens to be twice as much as the neutralization enthalpy of HCl. Now, why is this? Because sulfuric acid has 2 H pluses that can react with hydroxide ions. So 2 H pluses from one molecule would mean when enough and more sodium hydroxide is available, 2 H pluses will react with 2 OH minuses to produce 2 water molecules when 1 sulfuric acid mole reacts. 1 sulfuric acid mole will produce 2 moles of water. You can see that here. So the ratio is 1:2. So that is why the neutralization enthalpy of 1 mole of sulfuric acid happens to be negative 114 kilojoules per mole. And when it comes to neutralization of a similar reaction between sulfuric acid reacts with barium hydroxide, you can see the neutralization enthalpy is somewhat of a larger negative value, or magnitude of the enthalpy change is greater than 114 as well. So this is not just the enthalpy change of forming 2 water molecules. This should be there should be another reaction, and as you predict, you can see barium sulfate precipitate is formed, and this also contributes to having a greater magnitude of an enthalpy change over here. So then we move on to weak bases. When you're titrating weak bases, or when you're trying to find out the enthalpy change of weak bases, you can see weak bases would have a smaller energy release, so therefore enthalpy change is going to be less negative. Weak acids will also give off the same observation. It is not going to go up to negative 57 kilojoules per mole. It will stop around 55 or negative 55 kilojoules per mole. And over here, when you're trying to find out the neutralization enthalpy of barium hydroxide, it will be twice that of sodium hydroxide. This is because barium hydroxide releases 2 OH minus ions, and you would require 2 HCl moles to react with 1 mole of barium hydroxide to produce 2 moles of water. So 2 moles of water are produced, indicating that when you're neutralizing 1 mole of barium hydroxide, H plus and OH minus will get together to form 2 moles of water. So because of that, the neutralization enthalpy of 1 mole of barium hydroxide happens to be minus 114 kilojoules per mole. So we just had a look at some neutralization enthalpies of different acids and bases. It is now time to move on to the next slide. In the next slide, we are going to observe the reaction that we are going to do in our experiment. So to carry out the reaction, we would need these equipment and these chemicals that we have mentioned over here. We would need plastic cups and we would need a beaker, thermometer, glass rods. And students, if you can use a calorimeter, that will be better. A calorimeter is a device that is specifically designed to carry out reactions such as this reaction that we are going to be doing in this experiment, which will allow us to measure a more accurate temperature change when the reaction is taking place, which will allow us to calculate a more accurate enthalpy change. So a calorimeter, if you have in your labs, if you can use one, that will give you more accurate results. However, in the absence of a calorimeter, you can use a plastic cup and a beaker to produce a similar setup. So we have chemicals. We will be using 2 moles per decimeter cube concentrated sodium hydroxide, 2MHCl, 2M nitric acid, 2MKOH or potassium hydroxide, acetic acid and ammonium hydroxide in the same concentration, 2 moles per decimeter cube. And this is going to be our setup. So let's have a look at it. So we will be using this instead of a calorimeter. We will have 250 cubic centimeter beaker acting as our insulator, and then we will have a plastic cup again to make sure that the heat loss that is going to happen in this system is minimal. We are using a plastic cup, and then we are going to carry out our reaction in the plastic cup. So before I explain this setup, let me explain what is going to take place here. When we add the acid and the base into the plastic cup, as they react, they will carry out a neutralization reaction. As you know, neutralization reactions are energy releasing reactions. Energy will be released. So this released energy will be released onto the solution, and the solution will increase in temperature as the heat that is now additionally coming into the solution is going up. So the temperature of the solution will go up as the reaction keeps on giving heat to the solution. And apart from that, the container will absorb heat as well, and some amount of the heat will get lost into the surrounding. So to minimize the heat loss, we use an insulating material like plastic to conduct this experiment. If this material was something like metal, metals can conduct heat really well, which will result in a higher heat loss. So to minimize the heat loss, we will be using a plastic cup. And again, to insulate the system a little bit further, we will be placing this plastic cup in a beaker. And if you can actually cover this plastic cup when it is in the beaker with some insulating material like wool. That is also going to make sure that the heat loss is minimal. And we are going to cover it with a cover as well to make sure that there's no heat exiting from the open end of the system. And then through a hole on the cover, we will include our thermometer, or we will dip our thermometer into the solution as well as our stirrer, because we need to make sure the solution is properly mixed. So this is the setup, students. You can see the stirring rod, you can see the thermometer included in the system. So the bulb of the thermometer should be in the solution, And then we have the cover, plastic cup, and the beaker. And as you can see over here, students, the solution is present in the plastic cup, not in the beaker. So the reaction is taking place in the plastic cup. This setup would ensure that the heat loss is minimized. So these are the steps that you need to follow. Place a plastic cup into 250 cubic centimeter beaker as shown in the diagram. Add 50 cubic centimeters of 2m or 2 moles per decimeter cube HCl into the cup and measure the temperature. This is going to be the initial temperature of the acid. And then transfer 50 cubic centimeters of 2m sodium hydroxide into a beaker and measure the temperature. Majority of the time, students, if you are carrying out this reaction in room temperature conditions, both solution of the acid and the base is going to be the same. But if you freshly prepare sodium hydroxide, dissolving sodium hydroxide in water is an exothermic process. So at that point, sodium hydroxide temperature would slightly be higher. And dissolving HCl in water to produce the HCl solution is also an exothermic process. And at that point, HCl solution temperature might also be high. However, if you have prepared these solutions well in advance and allow them to come to room temperature, both of the solutions will usually have the same temperature at that point. So if in any situation the two solutions do not have the same temperature, then as the initial temperature of the reaction, you have to take the average between the two temperatures. So the initial temperature would be the average temperature between the initial temperature of HCl and initial temperature of sodium hydroxide. Add the above sodium hydroxide solution to the plastic cup containing HCl, and immediately after that you can close the lid and start recording the temperature each 30 seconds until maximum temperature value is reached. So we open the plastic cup lid and you add the sodium hydroxide to that of HCl that is already in the plastic cup, and as soon as you add it, you mix it quickly and you close the lid, and you can continue to stir it with the stirring rod, but you need to start observing the temperature. The temperature is going to go up quite fast, and you need to continuously monitor the temperature and how the temperature is increasing, and you have to note down the maximum temperature that was reached when the reaction was taking place. And then you have to repeat this same process for other acid-base couples. Make sure to clean the plastic cup between experiments and the thermometer and the glass rod before each experiment. Otherwise, what happens is, friends, you will introduce some amount of acid or base from previous experiment into your current experiment. To avoid doing that, you have to wash each of these equipment before you move on to the next experiment. So we are not going to only look at sodium hydroxide HCl neutralization, we are going to look at a couple of other acid-base neutralization reactions. So we will follow the same process. We'll take the acid into the cup first, and then we will add the base later. Before we mix the two together, we will measure their initial temperatures. So this is the process that we are going to follow when we are trying to measure the neutralization enthalpies of acid-base neutralization reactions. Some of the experimental results or reactions that are taking place are given here. Reaction 1 is between sodium hydroxide and HCl, so it will produce sodium chloride and water. This is for your reference, students. As two acids are mixed, you should know a salt and water is produced, and we have written down the balanced chemical equations for those reactions. So potassium hydroxide and nitric acid will produce potassium nitrate and water. Sodium hydroxide and acetic acid or ethanoic acid will produce sodium acetate, or we also can call it sodium ethanoate, and water. And you can observe the reaction ratios as well. Acid to water ratio is going to be 1:1. And the fourth reaction is HCl and ammonium hydroxide will produce ammonium chloride, the salt, and water. Finally, we have ethanoic acid and sodium hydroxide producing ammonium ethanoate and water. So these are the reactions that you will observe in our experiment. And this is how you will tabulate your observations or results. You will have to measure the temperature of the acid and the base solutions separately. And as I mentioned earlier, they might not have the same temperature. At that point, you have to get the average value of the two temperatures as the initial temperature of the mixture. So you have to note down the initial temperature, which is going to be given as T1. And then you have to note down the final temperature, which is T2. Right? Final temperature is going to be the maximum temperature that the system reached. That is your final temperature. And then we can calculate the temperature difference. Final temperature minus the initial temperature will give you the temperature difference. T2 minus T1. Now, we do know how to calculate the heat that was exchanged in this reaction. We learned earlier on today how to calculate the heat. Heat is heat absorbed or given off is normally calculated with the use of the equation Q equals mc delta T. So before we move on to that equation, we do make a few estimations. We estimate that the amount or number of moles of reactants in each case are known accurately. We think that the solutions that we prepared are accurate in their concentration, and we estimate that we do know the exact number of moles of each reactant present in the system. And we estimate the heat liberated during this reaction. So the specific heat capacity of water is this 4.2 joules per gram per Kelvin, and the density of water is taken to be 1.000 grams per cubic centimeter, right? So we can write the cubic centimeter part here. And the volume of solution is 200 cubic centimeters. Volume of solution is 200 cubic centimeters. So these are the estimations we make. And we also assume that there was no heat loss. So students, apart from that, we can also assume that all of the energy that was liberated or released was absorbed by the solution, and none of the heat was absorbed by the container when you are doing this experiment. So that is an assumption that we make in order to get to the neutralization enthalpy through this reaction. So the equation is Q, or the heat, is equal to mc delta T, mass of the system, multiplied by specific heat of the solution multiplied by the temperature change. So since we are using a total of 100 cubic centimeters, not 200 students, we are going to be using 100 cubic centimeters, as we will take 50 cubic centimeters of acid and 50 cubic centimeters of the base. So it's not 200 cubic centimeters, it's 100 cubic centimeters we are taking when we add 50 cubic centimeters of the acid and 50 cubic centimeters of the base together. Overall volume will be 100 cubic centimeters. And we consider the density of these solutions to be 1.000 grams per cubic centimeter. We consider the density of the solution to be the same as density of water. And then we will carry out this calculation. 100 cubic centimeters of water multiplied by its density will give us the mass. So what would be the mass? 100 grams. And then we know the specific heat capacity, which happens to be 4.2 joules per gram per Kelvin. And then when you're carrying out this reaction, your main focus is on measuring the temperature change. That is your task. When you're carrying out this titration, the main observation you should record is the temperature change. Initial temperature of the mixture as well as the maximum temperature the system reaches. So that difference is going to be your delta T. Now using these values, you can calculate your heat that was exchanged. In this case, that was released. And we know this is a heat release because the system increases in temperature. If the system decreased in temperature, that was a heat absorption. However, since we know we can write the heat released in this experiment can be calculated this way. Now, after calculating the heat released, you can proceed to calculating the overall or standard enthalpy change of neutralization of that particular acid-base reaction. So, to calculate this neutralization enthalpy of 1 mole of sodium hydroxide, you can use this particular equation. Enthalpy change is equal to the amount of heat released. To indicate that we are talking about heat release, we have the negative sign over here, right? I want you to observe that there is a negative sign over here. That is to indicate we are dealing with heat release. We are dealing with exothermic reaction. Divided by moles of the reactant which was acting as the limiting factor. In this case, we have taken both acid and base in the relevant number of moles. So you need to first calculate the number of moles we introduced into the system. If you move back, we see over here we are taking 2 moles per decimeters cube solution and we are taking 50 cubic centimeters of it. So if we roughly do a calculation over here, the number of moles is going to be equal to concentration multiplied by volume. Concentration is 2 moles per decimeters cube. And the volume is 50 cubic centimeters. 50 into 10 to the power minus 3. So then cubic centimeters is converted into decimeters cube that way. So you can see over here decimeters per decimeters cube cancel off, and 2 multiplied by 50 is going to be 100. 10 to the power minus 3 is there still. So this is the number of moles. If you solve it further, it's going to be 0.1 moles. So the amount of moles that we are going to be using of the acid and the base in this experiment is going to be 0.1 moles each of the acid and the base. So once you find out the heat that was released, if you divide the magnitude of the heat by our number of moles, you will get to the amount of heat that was released per mole of that acid or the base. And by including this negative sign, we will complete our standard enthalpy change of neutralization, and we will communicate that enthalpy value as a negative kilojoules per mole value. Those are the main theory parts that are revolving around today's experiment, and you have to know these theory parts before you move into the lab and actually conduct the experiment. So since we have covered these theory parts, it is now time for us to move on out of this classroom and into the lab to actually conduct our experiment. I will see you in the lab.
GCE Advanced Level Chemistry Practical Series, experiment number 7. Experimentational determination of the enthalpy of acid-base neutralization. In this practical, we aim to learn how to measure the temperature changes of a chemical reaction that is taking place, and later on, we are going to learn how to determine the enthalpy of an acid-base neutralization reaction. Now, let's move on to identifying the equipment and the reagents we will be using for this experiment. In this practical, the basic idea is to react an acid with a base and measure the highest temperature that particular reaction mixture reaches. So, for this purpose, we will be using a variety of acids and bases. Let's identify the bases we will be using for this practical. We will be using sodium hydroxide, potassium hydroxide, ammonium hydroxide. These are the three bases we will be using, and you can see the concentration of each of these solutions. Each of these solutions has a concentration of 2 moles per decimeters cube. And we'll be using 3 different types of acids as well. We'll be using HCl acid, we'll be using nitric acid, and we'll be using ethanoic acid. All of the acids also has the same concentration, which is 2 moles per decimeters cube. Apart from the acids, we'll be using a little bit of distilled water to wash the utensils we are using. We'll be using measuring cylinders to measure the acid and the base accurately. We'll be using a thermometer to measure the temperature accurately. And when the reaction is taking place, we need to make sure that all of the heat that is flowing into the system or out of the system is contained within the system. So therefore, we are using a heat insulated setup. What you see here is a plastic beaker, and inside the plastic beaker we have another plastic beaker with some insulation inside of the beaker, so that whatever the heat that is released or absorbed remains inside the system, and we do not release any heat towards the surrounding, or we do not absorb heat from the surrounding when this reaction is taking place, when we are conducting the experiment inside this setup. Apart from that, we will be using a thermometer that is directly included into this setup. We can see we have a lid here, and there's an opening. Inside this lid, we can see here, through these openings, we will be inserting our thermometer, and we have set up our thermometer on a retort stand. These are the equipment and our reagents we will be using for this experiment. Now, let's move on to actually conducting our experiment. In the first part of our experiment, we are going to see a reaction between HCl and sodium hydroxide. HCl is a strong acid and sodium hydroxide is a strong base. Now we are going to see the reaction between a strong acid and a strong base and measure the temperature increase when this reaction is happening. Normally, an acid-base reaction is an exothermic reaction. Exothermic reaction means as the reaction proceeds, energy will be given out of the reaction. Energy will be released from the reaction. This energy will be taken up by the water in the solution, and the temperature of the water will increase. When we are conducting this experiment, we are going to measure the temperature increase of this reaction. Due to the fact that we know the volume of the solutions we are using, we know the overall volume of the reaction mixture. Thereby, we know the overall volume of water that we are using here. And with the use of the temperature increase we can calculate the amount of heat that is released from the system. And as we carry this experiment out, we are conducting this experiment at atmospheric pressure conditions. So we assume that we subject this reaction mixture also into a constant atmospheric pressure condition. Now, let's move on to adding our HCl into this plastic container, and afterwards let's take the temperature readings of HCl and the sodium hydroxide we're adding to this reaction mixture. We have our measuring cylinder here, and let's take our HCl solution and let's add 50 milliliters of HCl into this beaker. As always, when measuring volumes, make sure to take the measuring cylinder to your eye level, otherwise you will not be measuring the right amount of solution. So we have measured the right volume here, which is 50 milliliters of HCl. Now we are going to be adding this 50 milliliters of HCl into this plastic beaker. Afterwards, we can lower this thermometer into our HCl solution. Now, let's take a look at the temperature reading of our HCl solution. The temperature reading of our HCl solution is 27 degrees Celsius. Let's move on to measuring the temperature reading of our sodium hydroxide solution. We have our sodium hydroxide solution here, and now we'll use a different thermometer and measure the temperature of the sodium hydroxide solution. The temperature of the sodium hydroxide solution is also at 27 degrees Celsius. Now, let's move on to the next step of our reaction. In our next step, we are going to measure 50 milliliters of sodium hydroxide solution. After measuring 50 milliliters of sodium hydroxide solution, we have to add the sodium hydroxide into this reaction mixture, and as soon as you do that, you have to measure the temperature increase of this reaction mixture. At the same time, you have to make sure that you close the lid of this container so that you won't have any heat loss through the top part of this beaker. We'll lift this thermometer out of the way, and we have to work fast at this point. We have to add our sodium hydroxide solution into this container, and as soon as we do that, we have to make sure that we close the lid and insert the thermometer into the reaction mixture to get a temperature reading. We'll place the lid like so, and we'll bring this thermometer down to the right level. As soon as we add the sodium hydroxide, all that is left to do is closing the lid. Now, let's add our sodium hydroxide solution. And we'll close this properly. Using a glass rod, we can stir the solution as well. Now you can see the temperature rising as the reaction proceeds. and we have to observe the highest temperature it reaches when the reaction starts to take place. Now the temperature is at 40 degrees Celsius. We have to observe the highest temperature that it reaches over the course of 1.5 to 2 minutes. Now, we observed when we initially mixed the hydrochloric acid with the sodium hydroxide solution, there was an increase in temperature all the way up to 40 degrees Celsius. And we observed if the temperature was increasing further than 40 degrees of Celsius. However, now it has started to come down. So the highest recorded temperature when this reaction was taking place was 40 degrees Celsius. After recording that temperature, we can move on to our next reaction. In the second part of our practical, we are going to be looking into a reaction between potassium hydroxide and nitric acid. Now, let's first measure 50 milliliters of nitric acid and transfer into our plastic container here. We have our nitric acid over here. We are going to take measuring cylinder and measure 50 milliliters of nitric acid. After measuring 50 milliliters of nitric acid, we are going to transfer this into this plastic container we have here, which is insulated. And now we are going to measure the temperature of our nitric acid. At the same time, we can measure the temperature of the base we are using. We are going to be using potassium hydroxide as our base. Now, let's take the temperature of potassium hydroxide as well. As you can see, the temperature of the acid is at 26 degrees Celsius and the temperature of the base is at 25 degrees Celsius. After recording the temperatures, we can now moving on to measuring 50 milliliters of our base. We have 50 milliliters of the potassium hydroxide base measured here. Now, we are going to add this 50 milliliters of potassium hydroxide to our nitric acid solution we have here. As soon as we add our potassium hydroxide solution into our nitric acid solution, we are going to record the highest temperature that this reaction mixture is going to reach. We have our potassium hydroxide. Now we are adding it to our nitric acid solution and we are going to measure the highest temperature that this reaction mixture is going to reach to. We can mix the solution a little bit as well. And we are going to observe the highest temperature this reaction mixture is going to reach to now. In this second part of our experiment, after reacting potassium hydroxide with nitric acid. We allow the reaction to proceed for about 2 minutes and we recorded the highest temperature that it has reached. According to our observations, the highest temperature that it has reached to is 38 degrees Celsius. Initial temperature of the acid was 26 degrees Celsius. Initial temperature of the base was 25 degrees Celsius. And the final highest temperature of the reaction mixture was 38 degrees Celsius. Now, after recording these temperature measurements, we can move on to our third part of this experiment. In the third part of our experiment, we are going to see an acid-base reaction between a strong base and a weak acid. We are going to use sodium hydroxide as our strong base, and we will be using ethanoic acid, or commonly known as acetic acid, as our weak acid. Both will have a concentration of 2 moles per decimeters cube concentration. And we are going to first measure 50 milliliters of ethanoic acid and transfer it into this beaker, and we are going to measure the temperature of the acid. Like before, we will be using a measuring cylinder, and we have our ethanoic acid here. We will take our ethanoic acid, and now we are going to measure 50 milliliters of this acid. Now we have measured 50 milliliters of that acid. Now let's transfer it into our beaker and measure the temperature. Now let's measure the temperature of the base as well. We will be using sodium hydroxide as our base. Let's take the base here, and we are going to use a different thermometer which has been washed since the last time we used it, and we are going to measure the temperature of the sodium hydroxide as well. You can see a side-by-side comparison of the two temperatures now. You can see on your left-hand side you have your weak acid, which is ethanoic acid. You can see the temperature of the ethanoic acid. And on your right-hand side you have your base, which is sodium hydroxide, which is a strong base. We observe the temperature of ethanoic acid as well as the sodium hydroxide we are using for this reaction. Both were at 26 degrees Celsius. Now we are going to measure 50 milliliters of sodium hydroxide using a measuring cylinder. And after measuring 50 milliliters of sodium hydroxide, we have to be prepared to close the lid of this setup and take a look at the highest temperature that the reaction mixture is reaching to. After getting ready to close the lid, we are going to be adding our sodium hydroxide to this acetic acid we have in the beaker. As soon as it is added, we are going to close the lid like so and take the temperature reading. We can mix the reaction mixture as well. And we are going to measure the highest temperature that this reaction mixture is going to reach. After allowing the reaction to run for a while, we observe the highest temperature that the system reached to. The highest temperature that the system reached to was 38 degrees Celsius. Now, we have to note down the initial temperatures of the solution. Both of the solutions were at 26 degrees Celsius. Now, after the reaction has gone to completion, the highest temperature that we recorded was 38 degrees Celsius. Now, let's move on to our final part of this practical. In our final part of this practical, we are going to observe a reaction between a strong acid and a weak base. For the strong acid, we have chosen hydrochloric acid, and for the weak base, we have chosen ammonium hydroxide. Now, let's measure 50 milliliters of hydrochloric acid and measure the temperature of our hydrochloric acid. We'll take our measuring cylinder here, and we have our hydrochloric acid, and let's measure 50 milliliters of hydrochloric acid. We have taken 50 milliliters of hydrochloric acid, and we are going to add this hydrochloric acid into our plastic container here. And let's measure the temperature. While we measure the temperature of our hydrochloric acid, we can take ammonium hydroxide that we have here and measure the temperature of our ammonium hydroxide solution as well, so that we can compare the temperatures side by side. You can see in our HCl solution, the temperature reading is 26 degrees Celsius. And in our ammonium hydroxide solution, the temperature is 24 degrees Celsius. Ammonium hydroxide solution is somewhat cooler than the HCl solution we have here. After noting down these temperature readings, we can move on to measuring 50 milliliters of ammonium hydroxide and adding it to our hydrochloric acid. Now, let's take a measuring cylinder and measure 50 milliliters of ammonium hydroxide. We have measured here 50 milliliters of ammonium hydroxide. Now, we are going to add this ammonium hydroxide into the HCl solution we have here in the plastic container, and we are going to close the lid and measure the temperature reading we obtain as soon as we mix the two reactants together. So let's add ammonium hydroxide into this container. And now you can see as the reaction proceeds, the temperature starts to increase. Now we can see towards the end of this reaction, we observed the temperature going up and coming down, and the highest temperature that this reaction mixture reached out to was 37.5. The initial temperature of the acid was 26 degrees Celsius. The initial temperature of the base was 24 degrees Celsius, and the highest temperature that the reaction mixture reached was 37.5 degrees Celsius. Let's move on to an additional reaction that we are going to show you in this experiment. In this additional part of our practical, we are going to take a look at the reaction between a weak acid and a weak base. For the weak acid, we have selected ethanoic acid, and for the weak base, we have selected ammonium hydroxide. Just like in the previous examples, we are going to measure 50 milliliters of our weak acid, which is acetic acid. So we have measured 50 milliliters of ethanoic acid, and now after measuring 50 milliliters of ethanoic acid, we are going to transfer it into our plastic beaker here, and we'll get the temperature of this ethanoic acid. We have our ammonium hydroxide solution here. We are going to measure the temperature of the ammonium hydroxide solution right next to our ethanoic acid solution. Now you can see the two temperatures here. Left hand side, we have the temperature of our acetic acid solution, which is 26 degrees Celsius, and on the right hand side, we have the temperature of the ammonium hydroxide solution, which is 22 degrees Celsius. Now let's move on to measuring 50 milliliters of our ammonium hydroxide solution. We have now measured 50 milliliters of ammonium hydroxide, and we are going to add that to this plastic beaker here, which is insulated, and we are going to measure the temperature change that takes place when we add our ammonium hydroxide solution. And let's measure the highest temperature that this reaction mixture reaches to. Now, we have allowed the reaction to take place for over 2 minutes, and we observe the highest temperature that it reaches to is 34 degrees Celsius. The acid had an initial temperature of 26 degrees Celsius. The base had an initial temperature of 22 degrees Celsius. And after mixing it, the final reaction mixture reaches a highest temperature of 34 degrees Celsius. After taking down these temperature readings, we can now move on to the enthalpy calculations and the important theory parts revolving around this experiment. Now, let's move on to the next session where we discuss the calculations.
Students, now in this session, we are going to be looking at some questions that are revolving around our experiment number 7, experimental determination of enthalpy of acid-base neutralization. So, in the initial parts of this practical or experiment, we had a look at the theory parts revolving around acid-base neutralization, and then we actually conducted the experiment, noted down the enthalpy changes, and here we are going to be now discussing some questions revolving around this experiment. Now, in this experiment, the first question we come across is given here. 250 cubic centimeters of 0.5 moles per decimeter cube sodium hydroxide and 250 cubic centimeters of 0.5 moles per decimeter cube HCl was reacted with one another, and the initial temperature of each of these solutions was 25 degrees Celsius. And when you react them, we have mixed them in a calorimeter. So let's read the whole sentence here. 250 cubic centimeters of 0.5 m sodium hydroxide and 250 cubic centimeters of 0.5 m HCl was with an initial temperature of 25 degrees Celsius was mixed together in a calorimeter. The final temperature of the mixture was 28.3 degrees Celsius. If the heat capacity of the container or the calorimeter was 46.2 joules per Kelvin, calculate the neutralization enthalpy of sodium hydroxide. In this question, we have been given all of the information we need to calculate the neutralization enthalpy of sodium hydroxide. So first, let's take a look at the reaction that is taking place. We have sodium hydroxide, NaOH, reacting with HCl. Now both of them are strong in the sense sodium hydroxide is a strong base. It fully dissociates in water, and HCl is also a strong acid. That acid also will fully dissociate in water, and it will form water and sodium chloride. And the underlying main equation, the ionic equation, is H plus and OH minus reacting to produce water. However, our main interest is going to be the first equation we wrote, sodium hydroxide reacting with HCl to produce water and sodium chloride, because we are going to be observing the neutralization of 1 mole, or that is what we are trying to calculate, the enthalpy of neutralization of 1 mole of sodium hydroxide. So when you react 1 mole of sodium hydroxide with 1 mole of HCl, you will be producing 1 mole of water, H2O. So students, after noting down what we need to calculate, let's take a look at how we get to this answer. They have given all of the volumes of the solutions as well as the initial temperature of the solution, and then finally the temperature or the final temperature as well. So let's note them down. So overall volume, final volume of the solution is going to be 500 cubic centimeters. Why is it 500 cubic centimeters? because we have mixed 250 cubic centimeter portions of both the acid and the base. So the final volume of the solution is going to be 500 cubic centimeters. So what would be the mass of this mixture? Mass of the mixture would be 500 cubic centimeters multiplied by density of these solutions. Usually students, when it comes to this type of questions, density of the solution is going to be equal to density of water, 1 gram per cubic decimeter. So we will make the assumption here as well. 1 gram per cubic decimeter is the density of these solutions, or 1 gram per cubic centimeter. 1 gram per cubic centimeter is the density of each of these solutions. So the water's density is also 1 gram per cubic centimeter, and over here as well, when it comes to these solutions, we take 1 gram per cubic centimeter to be the density of these solutions as well. So the mass of the mixture is going to be 500 grams. So now we have calculated the mass, and now it is time for us to calculate the temperature change. Over here, we can see the initial temperature was 25 degrees Celsius and the final temperature was 28.3 degrees Celsius. So final temperature minus the initial temperature, right? We can write TF minus T initial, 28.3 minus 25 degrees Celsius is going to give us a value of 3.3 degrees Celsius. So now we have calculated the mass and the temperature change. So it is time for us to calculate the heat that is released as this reaction was taking place. We know this is a neutralization reaction. So we know very well that heat was released. So heat released by the reaction, or we can say more precisely, instead of saying heat released by the reaction, we can say the heat energy absorbed by the solution, because we use solution's temperature increase for this calculation. So we can write heat absorbed. Heat absorbed by the solution. If you call it Q, it's going to be equal to mc delta T. So heat absorbed by the solution is a Q value. It is going to be equal to mass multiplied by specific heat capacity and temperature change. So mass is 500 grams, and we have learned when it comes to specific heat capacity of water, that is 4.2. 500 grams multiplied by 4.2 joules per gram per Kelvin. And then we have the temperature change, which is 3.3 Celsius. But when you're substituting, you can substitute in Kelvin, as I told you in the beginning of this experiment's theory part. Temperature difference in Kelvin is going to be equivalent to temperature differences in Celsius. Celsius and Kelvin temperature differences are going to be having the same value. So we can substitute this in Kelvin over here. So you can very clearly observe how the units cancel off. Per Kelvin, Kelvin cancels off. Per gram, gram cancels off. And then you are left with this multiplication. It's going to be 2100 multiplied by 3.3. The unit is joules. So when you multiply these two together, you get 6,930 joules. 6,930 joules. And if you convert this into kilojoules, it will be 6.93 kilojoules. So this is the energy that was absorbed by the solution. So students, if you want to have a look at what is taking place, as the reaction proceeds, due to the heat that is released from the reaction, the temperature went up from 25 degrees Celsius to 28.3 degrees Celsius. For this to take place, a certain amount of energy should have been absorbed by the solution. And the amount of energy that was absorbed by the solution is exactly 6.93 kilojoules of energy. Apart from the solution, of course, we have the container. In this case, we are using a calorimeter. So this calorimeter also absorbs a certain amount of energy, and we have been given the heat capacity of the calorimeter as well. So apart from the energy that was absorbed by the solution, calorimeter will also absorb a certain amount of energy. So let's calculate that energy. Heat absorbed by our calorimeter can be calculated by multiplying heat capacity along with temperature change. This is not specific heat, we are dealing with heat capacity here. So the heat capacity was 46.2 joules per Kelvin. The heat capacity was given as 46.2 joules per Kelvin. And the temperature change still remains the same, which is 3.3. That was the temperature change in the system. So over here, please observe how per Kelvin and Kelvin cancels off. When you are doing calculations, always substitute the units so that you can observe how the final unit is obtained, right? When you substitute the specific heat value in joules per Kelvin and then the temperature in Kelvin, you can very clearly observe the final answer comes in joules. So the final answer is the multiplication between the two. So it comes up to 152.46 joules. The final temperature comes up to 152.46 joules. Now students, after obtaining this value, we can move on to calculating the overall amount of energy that was released. Now we observed solution's temperature went up, as well as we can see calorimeter or the container temperature has also gone up, because this is all part of one system. So calorimeter has absorbed certain amount of energy as well as the solution. We calculate the solution's energy first, amount of energy that solution absorbed, and then we calculate the amount of energy that the calorimeter absorbed. So the overall amount of energy released when the reaction was going on is equal to energy absorbed by the calorimeter as well as the energy absorbed by the solution. So we can write that down. The total energy or heat released by the neutralisation is equal to heat absorbed by solution plus heat absorbed by calorimeter. So the heat that was absorbed by the solution we calculated earlier, it happened to be 6.93 kilojoules. So this is 6.93 kilojoules. And a little while ago, we calculated the heat absorbed by the calorimeter. Since it is in joules, we can convert it into kilojoules here by dividing it by 1000. So it happens to be 0.15 kilojoules at that point. So we can add that value over here, 0.15 kilojoules. 5 and 3 is 8, 1 and 9 is 10. So the final value is 7.08 kilojoules. So this is the total amount of energy, heat energy, that was released by this neutralization reaction. And now it is time to find out the enthalpy change of neutralization of sodium hydroxide using these details. So in the beginning of this question, they very clearly mentioned the amount of sodium hydroxide and HCl that we use. We have used 0.5 moles per decimeters cube concentrated sodium hydroxide, and we have used exactly 250 cubic centimeters of it. So now it is time for us to calculate the number of moles of sodium hydroxide. So the number of moles of sodium hydroxide, if you calculate the number of moles of sodium hydroxide, that will be equal to concentration multiplied by volume, 0.5 moles per decimeters cube multiplied by 0.25 decimeters cube. So I have directly converted 250 cubic centimeters into 0.25 decimeters cube. So 250 cubic centimeters, when divided by 1000, we can get to decimeters cube. So this is the value of the decimeters cube in volume that we took for this particular reaction. So the final answer is going to be 0.125 moles, 0.125 moles of sodium hydroxide. So we took the same concentration and same volume of HCl as well. So HCl number of moles will also be the same because we took the same concentration and the same volume of HCl. So according to our equation we wrote earlier, sodium hydroxide plus HCl, we have sodium chloride plus water. Since the ratio between sodium hydroxide and HCl is 1:1, and between sodium hydroxide and water is also 1:1, when 0.125 moles of both HCl and sodium hydroxide reacts, it will produce 0.125 moles of water as well. So all of the sodium hydroxide is now completely neutralized. So when this neutralization reaction was happening, the overall energy that was released was calculated. Overall energy from the entire reaction was calculated. And that happened to be our Q value. The Q represents in this case the overall amount of energy that was released. That was 7.08 kilojoules of energy. And we know enthalpy value of neutralization minus Q divided by the number of moles. So we have minus 7.08 kilojoules of energy divided by the number of moles of sodium hydroxide, in this case 0.125 moles. And we do know for a fact that all of these sodium hydroxide reacted because we did take the same concentration and same volume of the acid as well, ensuring that all of the sodium hydroxide reacted. So over here, students, one thing other than the values to keep in mind is including the sign. Sign should be negative. Sign should be negative. So when you carry out this calculation, it happens to be coming to a value of 56.64 kilojoules per mole. Kilojoules per mole. 56.64 kilojoules per mole is going to be the neutralization enthalpy of sodium hydroxide. So the amount of energy released when 1 mole of sodium hydroxide is neutralized is going to be 56.64 kilojoules per mole. So this is the neutralization enthalpy of sodium hydroxide. So students, this is the answer to our first question. So we can write it down here. The answer would be minus 56.64 kilojoules per mole. That is the answer to our first question. Let's move on to the next question. In the second question, we have another neutralization reaction. The temperature of 75 cubic centimeter volume of 0.2 moles per decimeter cube concentrated lithium hydroxide solution in a vacuum flask is 27 or 24.7 degrees Celsius. So we have 75 milliliters of lithium hydroxide solution, concentration is 0.2, and the temperature of the solution is 24.7 degrees Celsius. And we have another 75 portion solution of 0.2 moles per decimeter cube concentrated HCl solution at the same temperature, and we have allowed both of them to react. So the highest temperature recorded in the mixture was 26 degrees Celsius. And we are making another observation here. If the heat capacity of the flask is 42 joules per Kelvin, calculate the enthalpy of neutralization for lithium hydroxide. So we have been given a few pieces of information here: the concentration of lithium hydroxide and the volume, and we have concentration of HCl and its volume, and you can see both the concentrations are the same, the volumes are the same, and we can say the number of moles of HCl and lithium hydroxide are both going to be the same without even going into any calculation. Now this is because, students, you have prior knowledge about the fact that lithium hydroxide is going to release only one hydroxide ion, HCl is going to release only one H plus ion. Apart from that, you know, when concentration and volume of two solutions are the same, the number of moles that are present in each of those solutions of each substance is going to be the same. So after making that observation, you have to note that this particular flask or the container that we are carrying this reaction in absorbs a certain amount of heat, and the heat capacity, the overall amount of heat the flask will absorb to increase the temperature of the flask by 1 degree Celsius is going to be 42 joules per Kelvin or 42 joules per Celsius. So after that, they're asking us to carry out a calculation to find out the neutralization enthalpy of lithium hydroxide. So let's first write down the equation. Lithium hydroxide will react with our HCl strong acid to produce lithium chloride and liquid water. And then we observe that they are reacting in 1:1 ratio, and water is also going to be produced only one in the same ratio. So lithium hydroxide to water ratio is also going to be 1:1. We can now calculate the number of moles of lithium that we take into this reaction. Lithium hydroxide number of moles. So N lithium hydroxide is equal to concentration of lithium hydroxide solution multiplied by volume. Concentration over here is given as 0.2 moles per decimeters cube. And the volume is given to be 75 cubic centimeters. We need to convert it into decimeters cube. So you multiply it by 10 to the power minus 3. Or you can divide by 1000, the same. At this point, you would observe when you multiply 0.2 with 75, answer is going to be 15. And then decimeters cube or per decimeters cube and decimeters cube cancel off, and you are left with 10 to the power minus 3 more. We can simplify this answer. 0.015 moles. This is the number of moles of the lithium hydroxide that we take into our reaction mixture. So lithium hydroxide number of moles was equal to we saw lithium hydroxide number of moles, HCl number of moles, and water that is produced for all produced in the same ratio, 1:1:1. The reaction ratio between lithium hydroxide and HCl is 1:1, and ratio between the reactant and the product, lithium hydroxide and water, was 1:1 as well. As we have taken the same volume and same concentration of acid as well, we can without any doubt say the same amount of HCl number of moles will be here when you're comparing the number of moles of HCl and lithium hydroxide. It should be the same, students. This is because the concentration of lithium hydroxide solution and the volume that we took is identical to the concentration of HCl and the volume we took of HCl. So they are reacting in 1:1 ratio. The number of moles that are taken into the reaction mixture is the same. So the amount of HCl, amount of water that is produced is also going to be the same. 0.015 moles of water will be produced. So that's an observation to make. And then we can proceed to see the overall volume of the solution. Overall volume of the solution is 75 cubic centimeters added with another 75 cubic centimeter volume That means the overall volume is 150 cubic centimeters. What is the mass of the volume here? Overall mass of the solution that is formed when two portions of the acid and the base is mixed together is going to be given by multiplying the volume with density. Volume multiplied with density. Volume is 150 cubic centimeters, the final solution's volume. And density we take to be the density of water, as I explained earlier, 1.0 grams per cubic centimeter. Cubic centimeter cancels off. So the final answer is going to be 150 grams. Final answer is 150 grams. Now, after measuring or after calculating the mass of the solution, it is time for us to calculate the temperature change. Delta T is equal to T final minus T initial. The final temperature, according to the question, is 26 degrees Celsius and the initial temperature was 24.7 degrees Celsius. So 26 minus 24.7 degrees Celsius. The change in temperature is going to be 1.3. So then now the temperature change and the mass was calculated, and now all that is left for us to do is calculate the energy or the heat that was absorbed by the solution. So heat absorbed by the solution is equal to mc delta T. mc delta T. Mass, as we calculated earlier, was 150 grams. And we know when it comes to specific heat capacity of solution, it's taken as 4.2 joules per gram per Kelvin. And the temperature change was 1.3 Kelvin. Now students, again a simple reminder, when in a system, when a chemical reaction is taking place, if the reaction is releasing energy, that energy is going to be usually absorbed by the solution of that particular mixture and the container. So the reaction mixture is going to be in a container. In this case, it's a vacuum flask, and the reaction is taking place in aqueous medium. So the solution is going to absorb the energy released by the reaction. So there are two energy absorptions taking place: absorption of energy from the solution as well as the flask or as well as the container. So when you multiply all of these values together, the overall energy that is going to be absorbed by this solution is going to be, when you multiply all of them together, it's going to be 0.819 kilojoules. 0.819 kilojoules. So this is the energy absorbed by the solution. Then actually we can call this, let's say, Q1. And then we can move on to heat absorbed. Heat energy absorbed by our vacuum flask, or I can say container. is going to be equal to heat capacity C multiplied by temperature change. We'll call this Q2. Right? Previous one was Q1. So the heat capacity of the vacuum flask or the container was given as 42 joules per Kelvin. 42 joules per Kelvin. So at that point, we can calculate the heat absorbed by the vacuum flask. 42 joules per Kelvin multiplied by the temperature change, in this case 1.3 Kelvin. Then when you solve this, you will get to your heat absorbed by just the container, and that happens to be 0.0546 kilojoules. You will usually obtain this answer first in joules, and then you can convert it into kilojoules. The first answer that you actually get is 54.6 joules, and then afterwards when you divide by 1000, you get to the kilojoule value that I have over here, 0.0546 kilojoules. So the overall energy released by the reaction, or we can write overall heat released by the neutralization of lithium hydroxide in the solution is equal to Q1, energy absorbed by solution, plus Q2, energy absorbed by the container. So Q1 is 0.819 kilojoules and Q2 is 0.0546 kilojoules. So when you add them together, it will be this value. So first of all, we have to write this down, 0.0546 kilojoules. So we have 6 here, 4 and 9 is going to be 13, 5, 1 and 1 is going to be 7, and we are going to have 8 over here. This is the overall amount of energy released by this reaction. So this is the total amount of energy released when we mixed 75 cubic centimeter of lithium hydroxide and 75 cubic centimeters of the acid together, right? So in that neutralization reaction, the overall heat released is this. So now it is time for us to calculate the neutralization enthalpy, right? The enthalpy of neutralization of 1 mole lithium hydroxide is going to be given as minus Q divided by reactant, in this case lithium hydroxide, moles. So the overall amount of energy was 0.8736 kilojoules. Keep in mind it is negative because we have in the formula a negative sign built into the formula. And the total number of reactant moles we calculated earlier, and it happens to be 0.0 0.15 moles. So when you divide these two, you get to the answer 58.24 kilojoules per mole. Now students, we have value for the neutralization enthalpy of lithium hydroxide. But this value is slightly greater than our usual strong acid, strong base neutralization enthalpy, which is 57, minus 57 kilojoules per mole. And keep in mind students, this particular value should be minus or negative 58.24 kilojoules per mole. So we have obtained this answer that is a larger negative value than our usual strong acid, strong base neutralization. How is this happening? In this case, students, this greater negative value or enthalpy value that has a larger magnitude is a result of experimental error. So there could be a couple of experimental errors that go into producing an errorsome final answer like this. A couple of examples would be not having the correct value for the heat capacity of the container, or not being very sure of the concentration of the solution. Some of the errors could be not knowing the heat capacity of the container correctly, not having the correct concentration of the solutions, not measuring the correct volumes of each solution, are some of the errors that might be introduced into an experiment like this to get an errorsome result like this. So students, that is the answer to our second question. Now we are going to move on to our third question. So let's take a look at the third question. The neutralization enthalpy of 1 mole of sulfuric acid is negative 114 kilojoules per mole. 100 cubic centimeters of 0.2 moles per decimeter cube concentrated sodium hydroxide solution was reacted with 100 cubic centimeter portion of 0.1 m sulfuric acid solution. The initial temperature of both the solutions are the same. Okay, we are starting with the initial temperature that happens to be the same for both the solution. The first part of the question, they ask us to calculate the heat that will be liberated or released in the above reaction. And the second part of the question asks, considering that the heat capacity of the container is negligible and that there was no heat loss, calculate increase in temperature when the reaction was allowed to take place. So there are two questions. One, we need to calculate the heat that is going to be released when we react the sulfuric acid solution and our sodium hydroxide solution in these proportions. And then they're asking us to calculate the overall increase in temperature when we allow this reaction to take place. So let's take a look at the first question. So the first question is asking us to calculate the heat that is liberated. So over here we have this reaction taking place, sulfuric acid reacting with our sodium hydroxide solution. And we know we would need 2 sodium hydroxide over here. So the product is going to be Na2SO4. This is the salt and will form 2 water molecules. Each sulfuric has 2 H plus ions. So therefore, to 1 sulfuric acid, you would need 2 sodium hydroxide. And let's observe the number of moles of each to see whether we have this reaction ratio preserved. The ratio between sulfuric to sodium hydroxide is 1:2, and sulfuric to water is going to be 1:2 as well. So let's see if that reaction ratio is preserved when we mix the solutions in the above proportions. So let's calculate the number of moles of sulfuric acid. So the number of moles of sulfuric acid can be calculated with the use of this equation. And we have used a concentration of 0.1 for sulfuric acid, but 0.2 for sodium hydroxide. 0.1 moles per decimeters cube, and the volume was 100 cubic centimeters. So the number of moles of sulfuric acid would be, when you solve this, you can see decimeters cube cancel off, this becomes 0.1. So the final answer is 0.01. 100 divided by 1000 is 0.1. 0.1 multiplied by 0.1 is 0.01 moles. So since sulfuric acid to sodium hydroxide ratio is 1:2, if 0.01 moles of sulfuric acid reacts, how many moles of sodium hydroxide do we need to react with it? Twice as many. So that means we would need 0.02 moles. So now it is time for us to see if this many moles of sodium hydroxide was introduced into our reaction mixture. How do we calculate that? They have given us the concentration of sodium hydroxide. Concentration of sodium hydroxide happens to be 0.2 moles per decimeters cube, and volume is 100 cubic centimeters. So when you convert it in decimeters cube, it can be written like that. So 100 multiplied by 10 to the power minus 3 is 0.1. 0.1 multiplied by 0.2 happens to be 0.02 moles. So the number of moles of sodium hydroxide we have actually taken into our reaction mixture happens to be 0.02 moles. And that happens to be the exact number of moles we need to react with the sulfuric acid we added into the mixture. So all of the sulfuric acid completely reacts here. So now we know that the neutralization enthalpy of sulfuric acid, that means to neutralize, delta H, or we can write heat released when neutralization of sulfuric acid takes place. So H2SO4 neutralization enthalpy is given over here in the question, and the value is minus 114 kilojoules per mole. That means for a single mole of sulfuric acid, the neutralization enthalpy is minus or negative 114 kilojoules. So when you are calculating the energy released by just 0.01 mole of sulfuric, you can carry it out this way. Heat released by just 0.01 mole of H2SO4 is equal to the enthalpy of neutralization for sulfuric acid multiplied by the number of moles. So we have the number of moles written first, 0.01 mole multiplied by 100 negative 114 kilojoules per mole. You can see per mole and mole cancels off, and final answer is given as 1.14 kilojoules, and the value is still minus, indicating that this is an energy release that is taking place. So the overall energy release when this particular reaction that we were given in the question take place is minus 1.14 kilojoules, or energy released is 1.14 kilojoules. If you want to communicate as an enthalpy change, that is going to be minus 1.14 kilojoules. Now we move on to the next question. Considering that the heat capacity of the container is negligible and that there was no heat loss, calculate the increase in temperature. So we need to calculate the increase in temperature, and the main things that we need to keep in mind is that there was no heat loss and the container's heat capacity was negligible. So that means, students, when the reaction was taking place, all of the energy that is released was only taken up by the solution. Usually, when a reaction takes place, energy will be given off to the solution. Apart from that, some amount of energy will be given off to the container so that the container increases in temperature. And for example, when you pour hot water into a beaker or into a metal container, does the container remain cold to the touch, or does it increase in temperature? It does increase in temperature. And actually, after a while, both of the solution and the container will obtain some sort of thermal equilibrium where they both will be at the same temperature. Unless and otherwise you are filling warm liquid to a vacuum flask. At that point, the vacuum flask, if it has a good vacuum, will minimize the heat loss, and the flask will be at a different temperature. The outside of the flask actually will be at a different temperature. However, that's an exception to what we're talking about here. The heat given off by the reaction is going to be absorbed by the solution as well as the container. For example, if you pour hot water into a beaker or any other metal container, you would observe that the container will also obtain the same temperature as the liquid. This is because the liquid or the solution and our container will obtain a thermal equilibrium where their temperatures are going to be the same. So some amount of the heat from the reaction is given to both our solution as well as our container. And at the same time, some amount of our heat is going to be lost. So students, in this particular experiment, we assume that the container did not absorb any heat as well as that there was no heat loss. These are the two assumptions that is given to us in this question, that there's no heat loss and that the container does not absorb any heat. So we can make those assumptions and then move on to answering this question. Considering that the heat capacity of the container is negligible, calculate the temperature increase. So then at that point we can write heat released by the neutralization reaction is going to be equal to, directly, since we are assuming there's no heat loss and the container does not absorb any heat, it will directly be equal to heat absorbed by the solution. So we do know that the heat released by this entire neutralization, and that happens to be 1.14 kilojoules. Over here, there is no need to indicate the minus sign because we are not talking about enthalpy change. We are talking about the heat that was released. We are talking about heat here. So the amount of heat that was released is 1.14 kilojoules. We calculated in the previous step of this question, and is going to be equal to mc delta T. So we know Q, we know M, we know C. Only thing that we don't know is delta T. So delta T can be calculated by taking 1.14, which is the heat, or Q, that was released, divided by mass into the specific heat. Actually, now I can substitute the values. So I will go ahead and substitute the values over here. So in this reaction, what were the volumes that we used? We used 100 cubic centimeters of sulfuric acid as well as 100 cubic centimeters of our sodium hydroxide solution. And we know specific heat is going to be 4.2 joules per Kelvin. So since we use 200 cubic centimeters here, we know how to convert cubic centimeters of a solution into a mass. So 200 cubic centimeters is equal to 200 grams. So we can show that over here. Volume multiplied by density. Volume is 200 cubic centimeters. And density is 1 gram per cubic centimeter. So this is 200 grams. So we have 200 grams over here, multiplied by specific heat, 4.2 joules per Celsius, or joules per Kelvin. We can use both forms, no problem. So at this point, students, if you carry out the calculation, you will get to the temperature change, and when you do so, you get to 1.36 Kelvin. So this is the temperature change that you observe. So since we know this is the heat release, the temperature increase is going to be 1.36 Kelvin. Temperature increase is going to be 1.36 Kelvin. So the answer to this question, the increase in temperature, they're not asking the final temperature reading, they're asking for the increase in temperature, and that happens to be 1.36 Kelvin. We can say 1.36 degrees Celsius. Both are correct. Now let's move on to the next question. So now we are at the fourth question. A volume of 2.00 into 10 to the power 2, or in other words 200 cubic centimeters of 0.862 moles per decimeter cube HCl, and a volume of 200 cubic centimeters 0.431 moles per decimeter cube concentrated barium hydroxide was mixed in a calorimeter with negligible heat capacity. So what are they trying to communicate here? The heat capacity of the container is negligible, indicating that the container does not absorb any heat. The initial temperature of the solution, both of the solutions are given as 20.48. 20.48. If the enthalpy of the following process, this is the acid-base neutralization process, is 56.2 kilojoules per mole, calculate the highest temperature of the mixture. Now in this case, they have given us the neutralization enthalpy of a strong acid, strong base, and according to this question, it is negative 5 or 56.2 kilojoules per mole. So we have to use that value instead of the value that you are aware of, which is negative 57 kilojoules per mole. So H plus and OH minus, when they react 1 mole each to produce 1 mole of liquid water, according to this particular question, the neutralization enthalpy is negative 56.2 kilojoules per mole. So now they're asking us to calculate the highest temperature of the mixture. We need to calculate the highest temperature of the mixture. So first of all, students, we need to calculate how many of H plus ions are going to be mixed with how many of OH minus ions. So we do need to identify the presence or number of moles of H plus and number of moles of OH minus that are in the medium. And since we know when 1 mole of H plus and 1 mole of OH minus produce this much of heat, we can figure out, if we know the number of moles of H plus and OH minus in the medium, we can figure out the amount of energy that is going to be released. So let's move on to that first. So we are dealing with an acid, and the acid happens to be our usual HCl acid, and the concentration is given there, 0.862. So let's calculate the number of moles of HCl. Concentration is 0.862 moles per decimeters cube, and the volume is going to be, we have taken exactly 200 cubic centimeters. So that is going to be, I can write it like this as well, 200 cubic centimeters multiplied by 10 to the power minus 3. So then it becomes decimeters cube. So when you solve this volume, it is going to be 0.2 decimeters cube. So when you calculate the number of moles, it's going to be 4 here, 2, 16, and 17 over here, but there are 4 decimal places, so there should be 4 decimal places in the answer as well. So this is the number of moles, 0.1724. 0.1724 is going to be the number of moles of HCl we take into this reaction mixture. And then we'll move on to our barium hydroxide. Let's calculate the number of moles of barium hydroxide that we add. So what we're trying to observe is whether we have enough of H plus to react with what are the number of moles of barium hydroxide, or whether we have enough barium hydroxide to react with the number of moles of HCl that is in the reaction mixture. So again, we can use N equals Cv here. So concentration of barium hydroxide was 0.431 moles per decimeters cube, and the volume happens to be the same, 200 cubic centimeters. I will convert that into decimeters cube here. So when you do that, the answer would be, so 10 to the power minus 3 multiplied by 200 is going to be 0.2. 0.2 multiplied by 0.431 is going to obtain a value of So we'll multiply together. So 2 multiplied by 1 is 2, then 2 multiplied by 3 is 6, 2 multiplied by 4 is 8. 862 is going to be the answer, but this is 0.2. This whole thing solves out to be 0.2. And 0.2 multiplied by 0.431. So there are 4 decimal places, students. So in the answer, we have to have 4 decimal places as well. So the answer is 0.0862 moles. 0.0862 moles of barium hydroxide. But we need to keep one thing in mind. One barium hydroxide contains 2 hydroxide ions. So when barium hydroxide dissociates, it produces 1 barium 2 plus ion along with 2 hydroxide ions. So if the number of barium hydroxide is 0.0862 moles, when all of the barium hydroxide in water easily dissociate, it will produce twice as many number of moles of hydroxide ions as there are barium hydroxides. So you need to multiply this number by 2 to find out the number of moles of hydroxide ions that are coming into the medium. So let's multiply this number by 2. So if you multiply it by 2, there will be a 4 here, a 2 here, and 16 plus 1 is going to be 17. Altogether, the number of moles will be 0.1724 moles. So the hydroxide moles that are coming into the medium is going to be 0.1724, and over here we saw HCl number of moles is going to be the same, and we know with each HCl, if you write it over here, each HCl will release 1 H plus. So therefore HCl concentration equals, or HCl number of moles equals the amount of H plus that comes into the medium. So in the medium we have, on the reaction mixture, we have equal number of moles of H plus number of moles is this, and OH number of moles is also the same value. So that means we have H plus and OH minus ratio is going to be 0.1724 each. These are all in moles. So there are 4 students. They are reacting in their perfect 1:1 ratio. They have been mixed in the exact stoichiometric proportions. So after noticing that, we can now move on to identifying or calculating the overall amount of heat that is going to be released here. The overall amount of heat that is released is going to be equal to heat released by this neutralization is equal to heat released when 1 mole of H plus reacts with 1 mole of OH minus, and that heat happens to be, according to this question, 56.2 kilojoules per mole, according to the question. But we didn't have 1 mole of OH minus reacting with 1 mole of H plus here. We had actually 0.1724 moles of H plus reacting with the same amount of moles of OH minus. So the final answer will be obtained. When you multiply these two values, the final answer you get is 9.68 kilojoules. Now, we have worded this calculation, or we have phrased it, heat released. At that point, students, you don't actually have to include the minus sign over here, because we are talking about the amount of heat released by this particular reaction, and we have taken heat released when 1 mole of H plus reacted with 1 mole of OH minus. So you don't need the minus sign here. If you include that, you're actually going to get to an answer which is going to be also minus or negative in value, and that is because you can say we have calculated the enthalpy change that happens when this type of reaction takes place. So if you are communicating this answer as an enthalpy change, having the negative sign is going to be important. But if you are going to simply communicate it as a heat change, which we are going to be doing now, so heat release, in this case, heat release is going to be 9.68 kilojoules. So the sign, negative sign, is not important. If you have a negative sign, you are talking about the enthalpy change that took place when you were carrying out this reaction. So this was our heat change or heat release that happened when this reaction was taking place. So if you want to calculate the overall temperature change, you can use this equation. Overall amount of heat, in this case heat release, is equal to mass multiplied by specific heat multiplied by temperature change. And we have to calculate the mass. We know the specific heat is going to be 4.2, and we do know that we take 200 cubic centimeters of each solution. So the overall volume of the final solution is going to be 400 cubic centimeters, and the density value is going to be 1 gram per cubic centimeter. Actually, you can keep in mind that 1 gram of water equals, or 1 cubic centimeter of water equals 1 gram. So at that point, you know 400 cubic centimeters is equal to 400 grams. So we know the mass, we know specific heat. Only thing we don't know is this. We know the Q as well. We just calculated Q, the heat released in this particular reaction. So temperature change is equal to Q divided by MC. Now Q is 9.68 kilojoules divided by MC. Mass is 400 grams, and specific heat is going to be 4.2 joules per gram. So then, students, when you calculate using these values, the temperature change is going to come up to be 5.76 Kelvin. 5.76 Kelvin. This is your temperature change. Then, is this your final answer? Is this a question that that is being asked of us? The question is, the highest temperature that the mixture reaches is going to be the question that they ask here. So we need to calculate the final temperature or the highest temperature. Temperature change is equal to final temperature minus your initial temperature. We know the temperature change, we know the initial temperature, we don't know the final temperature. So final temperature is going to be equal to temperature change plus initial temperature, or initial temperature plus the temperature change. Initial temperature is, I will write it in that order so it will be more clear to you. Initial temperature plus the temperature change. Since it's the temperature increase, you will very clearly see the final temperature is a higher temperature than initial temperature. So initial temperature is 20.5 2.48 degrees Celsius, and we have to add to it our temperature increase. We saw it as 5.76 Kelvin, but temperature changes in Kelvin and Celsius are going to be equal to one another. So therefore, we can directly write 5.76 Celsius, because this is a temperature increase. So it's going to be, the final answer is going to be for over here 26.24 degrees Celsius, 26.24 degrees Celsius. So this is your final answer, students. The maximum temperature that your solution reaches is going to be 26.24 degrees Celsius. Now we are done with our fourth question. We can move on to the next question. Now let's move on to this final question. 50 cubic centimeters of 1 moles per decimeter cube sodium hydroxide and 50 cubic centimeters of HCl solution was mixed in a calorimeter with a negligible heat capacity. What does that mean, students? Negligible heat capacity means whatever the temperature increase that is going to be observed in this particular reaction is due to all of the reaction's energy being absorbed by the solution. So that means we assume that there's no heat loss, and we assume that there was no absorption of energy from the calorimeter. A temperature increase of 6.8 degrees Celsius was recorded. And then if 0.1 moles per decimeter cube of formic acid or methanoic acid was used instead of HCl, the temperature increase is only going to be 5.3. Only thing that we changed was the acid. The concentrations remain the same, right? So we used the same volumes, we used the same concentrations, but the acid was changed. At that point, the temperature increase was different. They are asking you, using this information, to calculate the dissociation enthalpy of methanoic acid. Let's go ahead and do that. In this question, we first have to find out the energy that is raised by the strong acid, and then strong acid, strong base neutralization. And then we need to move on to finding out the energy released by weak acid, strong base neutralization. And the difference between these two energies is going to be that the energy that was absorbed by the weak acid to dissociate the weak acid. So those are going to be the steps of this particular question. So let's go ahead and do it. The equation HCl plus NaOH forms NaCl plus water, and the underlying equation over here is H plus and OH minus turning into H2O. So let's calculate the overall energy release that is taking place over here. You are mixing two 50 cubic centimeter portions, so the overall volume is going to be 100 cubic centimeters, and we know if that is the overall volume, the mass of the solution is going to be 100 grams. We know how to carry out the simple conversion between volume to mass. And then the temperature increase was 6.8 degrees Celsius. Temperature increase was 6.8 degrees Celsius. So using that, we can now calculate the heat release by the neutralization. Heat released by the neutralization is going to be equal to mc delta T. Mass is going to be 100 grams as we calculated earlier. We have a specific heat capacity of 4.2 joules per gram. Joules per gram per Kelvin is the unit, joules per gram per Kelvin. And temperature change is 6.8 degrees Celsius. We can write it as Kelvin. Temperature changes, when it comes to temperature changes, Kelvin values and Celsius values are both equal. So when you carry out this calculation, the answer comes to 2856 joules. 2856 joules. So this is the amount of energy released by the reaction. And if you want to convert into kilojoules, you can do so by dividing by 1000, so you get to this kilojoule value. Now in this situation, students, the increase in temperature of the solution was there due to all of the reaction's energy released being absorbed by the solution. Usually when the reaction is taking place, energy release is going to be absorbed by the solution and then by the container, and then some energy is going to be lost to the environment or to the surrounding. But in this question, they say assume there's no heat loss and that the container is not absorbing any energy. They asked us to consider that the container's heat capacity is negligible, indirectly denoting the fact that container does not absorb any energy. So this heat that is going to be released is equal to the heat this heat that is absorbed by the solution is equal to the heat that is released by the entire reaction. So that is why we write heat released by the neutralization is equal to directly this value. Now afterwards, students, we can use this to calculate the neutralization enthalpy of HCl. We can write the neutralization enthalpy of HCl. Is equal to minus Q divided by reactant. In this case, HCl, reactant moles. So in this case, minus 2.856 kilojoules divided by number of reactant moles. So we do have to calculate the number of reactant moles. We do know we take 1 moles per decimeter cube concentrated HCl and sodium hydroxide, and we know they are in the right number of moles, and the volume is 50 cubic centimeters. So we can calculate the number of moles of HCl we take. So if you quickly calculate it here, HCl number of moles is going to be concentration multiplied by volume. Concentration is 1 moles per decimeters cube. And volume is going to be 0.05 decimeters cube. We can directly convert that into decimeters cube and write. Instead of writing 50 cubic centimeters, we have to convert it into decimeters cube. So when you convert it into decimeters cube, this is going to be the value. So the number of moles is going to be directly 0.05 moles. And since we took the same concentration of sodium hydroxide and same volume of sodium hydroxide, the number of sodium hydroxide moles that is in the mixture is going to be the same. So now we have the number of moles And the final answer when you carry out this calculation would be 57.12 kilojoules per mole. 57.12 kilojoules per mole. So this is a strong acid, strong base neutralization. So this is usually your standard neutralization enthalpy, which is 57.12 kilojoules per mole, or we usually say 57 kilojoules per mole. And you have to observe that the final answer is missing something here. What is that? This is a standard enthalpy change we are talking about. So the sign we included in the beginning of the equation should be here as well. So earlier on we haven't included, so you need to add it to the final answer. You can see the equation itself has a negative sign built in, negative Q divided by reactant number of moles, and then the final answer should contain that negative sign. Otherwise this answer would be wrong. So what is the neutralization enthalpy of HCl? It's going to be negative 57.12 kilojoules per mole. And finally, students, we move on to the heat released by methanoic acid based titration. You will produce so again you will observe that they are reacting in 1:1 ratio, and we have taken precaution in this question to mix them in the right number of moles. So students, if you go ahead and calculate them, you would observe that the number of moles over here is 0.05 moles, as we saw earlier in the previous step of this question, and the number of moles of formic acid or methanoic acid is going to be the same, because we take 1 mole concentrated formic acid and we take 50 cubic centimeters of it. So it's the same calculation as we saw earlier. The number of moles is going to be the same. So let's calculate the amount of heat released by this particular neutralization. And that is going to be so we'll call this Q. At that point, Q is going to be equal to mc delta T. We saw earlier the mass of the solution is going to be 100 cubic centimeters, or volume of the solution is going to be 100 cubic centimeters. So therefore the mass is going to be 100 grams. Specific heat is 4.2 joules per gram per Kelvin. And finally, the temperature change is going to be, in this question, it says the temperature change was only 5.3 degrees when it comes to the weak acid strong base neutralization. So temperature change is 5.3 degrees Celsius. So we can convert it into Kelvin and write here. So when you carry out this calculation, you will observe that the overall amount of heat that is released is 226 joules. We can convert this into kilojoules by dividing this by 1000, and it will become 2.226 kilojoules. Now students, we can move on to actually calculating the neutralization enthalpy for methanoic acid. methanoic acid. Should be methanoic acid. So students, we are dealing with methanoic acid or formic acid. So enthalpy of neutralization of methanoic acid would indicate the amount of energy that is going to be, or enthalpy change that is going to be observed when 1 mole of methanoic acid reacts with strong base. So over here the equation is minus Q divided by a reactant moles, in this case methanoic acid moles. So methanoic acid, when reacted with the strong base in the previous experiment, we saw it release 2.226 kilojoules of energy, and the number of methanoic acid moles that were present were 0.05. And when you solve this calculation, the answer would be minus 44.52 kilojoules per mole. Now, in other words, when you are neutralizing 1 mole of formic acid with a strong base, the overall enthalpy change happens to be negative 44.52 kilojoules per mole. And when we are neutralizing 1 mole of HCl with a strong base, it happens to be 57.12 kilojoules per mole. So let's see neutralization enthalpy of HCl. Neutralization enthalpy delta H note neutralization enthalpy of HCl happens to be 57.12 kilojoules per mole. We are assuming that these were done under standard conditions and at constant pressure. And neutralization of HCOOH formic acid happens to be 44.52 kilojoules per mole. So that means when 1 mole of formic acid is neutralized, this is the overall amount of energy that was released. When 1 mole of HCl was neutralized, a large amount of energy was released. What happened to the difference? Because the underlying reaction that is taking place is the same. H plus reacting with OH minus to produce 1 mole of liquid water. 1 mole of H plus, 1 mole of OH minus produces 1 mole of liquid water. And this releases this much of energy. But when it comes to the weak acid, some amount of that energy is not recorded here. What happened to that portion of the energy? That portion of the energy was the energy used for the dissociation of the weak acid. So the difference between these two energy values is your dissociation enthalpy for formic acid. So the difference between the two can be calculated. It happens to be 12.6 kilojoules per mole. Now, dissociation of a weak acid is going to be an energy absorbing process, so this is going to be a positive value. So this is going to be your dissociation enthalpy of methanoic acid, and that happens to be 12.6 kilojoules per mole, and this is a positive value. Now students, the final answer to this question is 12.6 kilojoules per mole. This is going to be your final answer to this question. Dissociation enthalpy of formic acid or methanoic acid is 12.6 kilojoules per mole. And with this, students, we conclude today's experiment. And in the beginning, we discussed the theory parts revolving around the experiment, and we conducted the experiment later on in the lab. And here we discuss some important questions that are revolving around this theory part. So with that, we will conclude today's experiment. I will see you again in the next experiment.